Hey everyone, today we have a race between three snails. Our goal is to design a circuit that identifies which snail reaches the finish line first. Importantly, once the first snail arrives, the circuit must lock in the winner, even if the other snails arrive later. To begin, let's understand how many output our system needs. Since the largest number is 3, and in binary it's 1, 1, we will need 2 output bits to encode the winner. Let's create a truth table that captures the basic behavior of our system. There are 4 possible outputs. No winner yet, output is 0. Snail 1 win, output is 1. Snail 2 wins, output is 2. Snail 3 wins, output is 3. So looking at the truth table, we understand that we have F0, which is OR between S1 and S3, and F1, which is an OR gate between S2 and S3. Hey, if you're finding this helpful so far, do me a quick favor. Hit that subscribe button down below. It really helps the channel. Hey, we want the system to remember the first snail that won, even if other snails arrive later. Let's say snail 1 wins, and we set the output to 1, 0 binary for 1. But if snail 2 arrives shortly after, the system might update the output to 1, 0 binary for 2, or even worse, ends up with 1, 1, which falsely indicates snail 3 won. To prevent this, we need a locking mechanism, one that says the race is over, we have a winner, ignore all other inputs. To achieve this, we will use flip-flops to store the winner and ensure the value doesn't change. In this exercise, we'll use the flip-flop. Let's break down how we build the system from here. We will use the flip-flops to store the result. Initially, they are set to 0, since there is no winner yet. We will use OR gate to detect if any flip-flop is set, which tells us that we already have a winner. This creates two states: race ongoing, no winner yet, 0, race complete, winner has been recorded, the result of the OR gate will be 1. To choose between those two states, we will use a multiplexer. There is no winner, we pass the output of the combinational logic to the flip-flops. Once a winner is detected, the MOOC select the stored value, effectively freezing the result and ignoring any new arrivals. Let's run a simulation. At the initial state, the output is 0, 0, which means no snail has crossed the finish line yet. As we can see, the system stays at 0, 0 as long as no snail reaches the finish line. The circuit waits for a change in one of the inputs. As you can see, as long as there is no change in the inputs, the system is stable, and the outputs are 0, 0, indicating no one arrived to the finish line yet. Let's say snail 2 wins the race. Let's observe what happens next. At this moment, the lower MOOCs passes the value 1, which corresponds to snail 2. This value is moving forward through the multiplexer to the D flip-flop. This value is now stored in the D flip-flop, and it also propagates to the OR gate, which now outputs 1, indicating we have a winner. The 1 from the OR gate sets the select line of the MOOCs to lock mode. This means the flip-flops now hold their value and no new input can override it. Even if other snails arrive, it's going to remain the same value, which is 1, 0, meaning snail 2 won.